Okay, so in this problem, we're looking to find the shear and moment diagrams along the span of the beam here from A to C. So the first step to all these problems is always find the support reactions. And in this problem, we're given that A has a thrust bearing in it, which means a thrust bearing exerts a force both in the Y direction and in the X direction. And we're given that at C is a journal bearing. Journal bearings do not prohibit any motion in the axial direction. So it only has a vertical support CY. Okay, so I think, so we would perform the equilibrium equations here to solve this. I think because of symmetry, I think you can see what's going to happen here. AX equals 0. And due to 5 kilonewtons being downward right in the middle, we have AY is going to equal 2.5 kilonewtons and CY is going to equal 2.5 kilonewtons. So I'm just going to fast track the equilibrium equations to find the supports. Now, the next point is we need to break this thing and perform method of sections. Okay, and this will be a piecewise function. So if we start at A and move down the beam, we have to perform a different method of sections every time there's an external load applied. So for example here, we need to break this in between A and B because there's a 5 kilonewton load applied at B, and then we need to break it in between B and C. So we have to perform this analysis in 2 steps here. If there are more loadings across here, we would have to perform more piecewise functions to get the entire shear and moment diagrams along the span of the beam. Okay, so here we go. So the next step is we would want to break it in between A and B and draw that free body diagram. So I'm just going to draw that free body diagram quick. We have 2.5 kilonewtons upward here. We have the normal, I guess we're not concerned with the normal force, so I'm not even going to draw that. The shear force is downward, and the moment here is here. So, and this distance here is x, all right? We're not solving it at a specific point. We're solving it by x. So x is across here. So by doing this, we sum the forces in the y direction and set those equal to 0. And we have 2.5 upward and our shear force downward. And that is it. We set that equal to 0. And our shear is going to be 2.5 in between A and B. So we can say that this is applicable in between 0 for x is in between 0 and 2. Okay, so this equation applies between A and B here. Now let's sum the moments around our point X. So we're going to sum the moments around point X, which is right here, and call counterclockwise positive. And we have M, which is counterclockwise. And then we will have this 2.5 generates a moment that is clockwise, so that will be negative, so 2.5. And then the distance that it acts away here is actually x, all right? So if x is from here to here, that is actually the moment arm, so we put in x there and set that equal to 0. So we get m is equal to 2.5x, right? 2.5x, let's make sure that's right. Yeah, okay. So now we have solved for the equations in between A and B. Now we must solve for the equations in between B and C. So here we're gonna say, these are the equations that apply in between x is between 2 and 4 meters. So we're looking at this part over here. So to do this, we need to draw the entire left-hand side of the beam. So this time it's going to be a little bit longer. This distance to where we've broken the section is still x. And we still have 2.5 upward. And we have our shear downward and our moment, but we must also include this force at B, which is 5 kilonewtons. So we have downward here, 5, and that distance there is 2 meters. So that's 2 meters. Oh, 2 meters. Okay. So that gets a little messy here, but we can solve this. So let's sum the forces in the y direction first and set those equal to 0. So we have 2.5 up, -5. We have 5 downward here, so that's -5. And then we have negative v, downward v for our shear force, and set that equal to 0. And solving that equation, we have v turns out to be -2.5, I believe. All right. And then we need to sum the moments. So let's sum the moments around x again. So x is this point over here, summing the moments around x. And we have counterclockwise the positive sign convention. So we have m counterclockwise. And then we have 2.5, which is going to be a clockwise moment. So that's going to be -2.5. And the distance that's acting away is x. All right, and now we have to take into account this 5 here. That's going to create a clockwise or counterclockwise moment, so that will be positive. And what is the distance that 5 is acting away? Well, if the entire distance is x, and this is 2 meters, that is x minus 2. Okay, so this entire distance minus 2, and that's this moment arm over here. Okay, and set that equal to 0, and we get a moment here, which is 10 minus 2.5x when we distribute this out and solve for m. So that is our moment. Okay, so we have all of these answers here. And now to create our shear and moment diagrams, all we need to do is plot these. All right, so let's start with the shear. Let's see if I can draw an axis here, okay? Okay. All right, so we'll say 4 meters is all the way out here, which makes 2 somewhere in here. Okay, from 0 to 2 for our shear, let's go back up and take a look. It's 2.5. So a constant 2.5. So we'll label this 2.5 here. And to 2. And then from 2 to 4 here, when x is equal to 2 to 4, we have negative 2.5. So the shear is negative 2.5. So we plot that from 2 to 4. Okay. So we'll just connect all these up. All right, so that is our shear diagram. All right, so as you see, it goes from 2.5 down to negative 2.5, and the difference between those, as you see, is 5. Okay, and the support reactions here is 2.5 upward, and we go down 5, and then we come over here, and then it's 2.5 positive on the other support. So that's another way to check your answer. And now let's talk about the moment. So I'm going to draw the same axis. Maybe. Okay. All right, so we have 4 here, 2, right around there. Okay, so let's take a look at the moment. And the moment from 0 to 2 is 2.5x. So it will have a slope of 2.5. So if we draw that all the way to 2, the slope's 2.5, and that value should be 2.5 times 2. That should be 5 kilonewton meters. And then from 2 to 4, we have this equation, 10 minus 2.5x. So if we put 2 into this equation here for x, that's 10 minus 2.5 times 2, so that's 5. So it lines up right here at 5 at the value of 2. And then at the value of 4, right, 2.5 times 4, this value turns out to be 10. So we have 10 minus 10, and that's 0. So it goes from 5 down to 0. If I could draw that. Okay, so that is our moment diagram. And to double check this, we can see that if we take the slope here, which is 2.5, that should be the value here. And then the value here is negative 2.5, and that is also the slope of this line. So that's a simple example of how to draw shear and moment diagrams.